Welcome back everyone, my name is Pedram and this is where we do advanced time series analysis, deep forecasting. Alright, let's do module number 3. This is going to be a lengthy one. I'm going to do it in 4 lecture videos. The first 3 ones are going to be the theory, and then the very last one is application in Python. So this is the very first one. I call it module 3 part 0, introduction to exponential smoothing methods versus ETS models. So let's dive into that. All right, let's begin our module number 3, exponential smoothing. So these are statistical methods that are going to create our point estimates or our forecast into the future. So if this is your, let's say, if this is your time series, we have time here, you have your Y, and imagine you have a time series like this, right? These exponential smoothing methods are going to go ahead and create point forecast for you. So for example, what is the prediction in H is equal to 1, forecast horizon 1. What about horizon 2, horizon 3, horizon 4, and etc. So these are what we call point estimates, right? Exponential smoothing methods, let me actually use the terminology method, are statistical tools that are going to enable us to train the model, let's say train the algorithm and then create point forecasts. So these red dots are the point forecasts. However, later on in this module, we're going to extend this idea and extend these methods to ETS models, right? So let me actually use another color. So we're going to extend them to ETS models. I want you to pay attention to the terminology that I'm using, models versus methods. Methods are going to only give us the point forecast, point estimates, but the models, because we're going to make an assumption about the residuals, we basically say that the residuals are normally distributed. And with that, we're going to be able to estimate the variance of those residuals. And later on, we're going to use those variance of residuals to create prediction intervals for us, right? So the difference between ETS model and exponential smoothing method is that, well, similarity is both of them are going to give you point predictions, and the point predictions are pretty much the same because the methodology is the same. However, the ETS model is also able to give you, I can connect it, right? It also able to give you some prediction intervals as well, right? So for example, well, it can be, let me actually make it another color. So actually I can highlight it, right? So it's going to give you prediction interval as well. So as we go further into the future, those intervals are going to become wider and wider. All right, so this is the terminology that right away I want you to pay attention. We're going to do this this module in 2 theoretical videos, one going over exponential smoothing methods and the other one going over ETS models. And now you know the difference. Both of them are going to give you the exact point estimate, but one of them, which is ETS model, is going to give you prediction intervals as well. Let me actually write down this prediction interval that you know what we're talking about, right? So let's use the blue color. Yeah, these are our prediction intervals, right? Prediction intervals. All right. All right, before we move forward with the exponential smoothing methods and ETS models, let's clear some forecasting notations first. So this at the top is basically what let me actually use my blue one. Okay, so these are the predictions. So that's why we use a hat. So these are the predictions at time t plus h. H is for your forecast horizon, given the information at time t. So this is how you should read it, right? And we say that these predictions are a function of basically your time horizon, how many steps you want to forecast into the future, and YT. And this can be a combination of, you can decompose this YT, right? You can decompose it to, for example, to trend, to seasonality. You can even include some lag values as well. So when you see YT here, just for simplicity, I only put YT, but be aware it can be anything. It can be lag values, YT minus 1, YT minus 2, and etc. And it can also be trend, seasonality, and you name it, right? So this itself can be anything. All right, so YT can be decomposed, as I said, into different components, 11 trend, seasonality. So that's what I was just talking about. And from this formula, again, this is just a notation. And the fitted values are calculated when H is equal to 0, right? So because you want to see what is the fitted value, so you put H is equal to 0, so the formula for your fitted value is going to become something like this, right? So it's going to be Y hat at time t. So this is conditional on t minus 1. That makes sense, right? So this is going to be a function of y t minus 1, and let's say your h is equal to 0, right? So that's going to be something like this. Again, this y t minus 1, this can include also the lag terms and different components as well. So just keep that in mind. Then if you want to do some one step ahead forecast, so basically you need to put h is equal to 1, and that forecast can be a time, for example, capital letter T. So here, let's actually show you the timeline. So this is your timeline. Let's say you have, this is your history going from number 1 all the way to number 10. So this is where we are right now. So let me actually say right now. And now you want to make forecasts into the future, right? So let me actually let's color code this one. So let's talk about one step ahead. So if you're at time t, the one step ahead is going to be t plus 1, right? Then the next time, let's say this is our observation, well, time step 11. This is my t plus 1. Then later, I'm going to be at this. So this is going to become my t, and then t plus 1 is going to be next time horizon, right? So this is 11, this is 12. You get the idea. So this is one step ahead forecast, right? We use the h is equal to 1 and we forecast into the future. And we have to, and we talked about it in module 1 as well. If you want to do one step ahead forecast, you need all the information until yesterday, right? To make a prediction for today. Or you need all the information until today to make a prediction for tomorrow. All right, then the next one is multi-step. So for multi-step ahead, we can change that h. So for example, h is equal to 2, we're going to do forecast 2 horizon into the future, 4 horizon into the future, and etc. And if you remember from module 1, we can do it in 2 ways. We can make those forecasts into the future one output at a time, or we can do multi-output at once, right? So let me actually show you. Let's start with one output at a time. So this means that if you're at time t, and I'm going to do one output at a time multi-step, right? So my next prediction is going to be this. And later on, I'm going to use this prediction for the next one. So it's basically iteratively going through multiple one step ahead forecasts, right? So this is as if you put one step forecast in a for loop, right? So then use this information to make a forecast for this, use this information to make a forecast for this. And as you can see, this is iterative. This is one output at a time. Versus, let me use red, versus if you want to do multi-output at once. Let's say we are at time t, and then you want to predict, the forecasting horizon 1, 2, 3, 4, or basically time index 11, 12, 13, 14, all at once. So this thing is going to be produced, all the forecasts are going to be produced at once, if that makes sense. So hopefully this kind of notation makes sense. All right. So basically what I want you to take away from this slide is that using this formula, we can figure out what are the fitted values, and forecasts. So the fitted values, we're going to say it's going to be called y hat t, and given t minus 1 is equal to a function of y t minus 1. That's it. And then your forecast, if you're assuming that you're at terminal point, capital letter T, given, well, actually we're forecasting into the future as well, right? We're forecasting h step into the future, given t is equal to f y t and h. All right, so we're gonna need these two formulas, notations, fitted values versus forecast in the future. Okay, so this chapter, this module is all about moving averages. We want to be somewhere in between two extreme cases. One is our very own naive forecaster, and the other one is simple average, right? So when we're talking about exponential smoothing or ETS models, remember those point forecasts, those predictions are somewhere in between these two extreme cases. So remember from module 1, when we talked about naive forecast, let me actually write the naive forecast in terms of the new notation that we're talking about. So it's going to be y hat t plus h given t. And as you can see, it's independent of your time horizon. So it's the last value. So basically, we talked about it in module 1 as well. Naive forecast is if you want to say what is the price, for example, for tomorrow, then you're going to take today's price as your forecast. And you're going to use that price infinitely into the future. So that's why it's independent of age, right? So here's the Google daily closing price, for example, in this chart. And then if I want to show you what is a naive forecaster, look at that. Imagine this part is your test set. This part is your train. And then we are here, and then I want to project into the future. So what is the last observation? The last observation is this, and let me use the right color. And I'm going to project it into the future. So this is my YT, my naive forecaster. Okay. Then on the other extreme, we are going to look into simple average, right? So let's use, let's talk about simple averages using this notation, right? So again, predictions of t plus h given t is a simple weighted average, and the weights are all equal, right? Of all the previous information. So I have a historical data, and I simply take the average, and the average is somewhere around this. And as you can see, this also is independent of H. You don't see letter H here. So these are your, and we talked about them as benchmarks, right? And as you can see, you can think of both of these benchmarks as weighted averages. The first one, we're putting all the weights on the last observation. The second one, we are equally sharing the weights between all the observations. So what we need is something in between, right? So we need to, basically this exponential smoothing methods or ETS models that we're going to talk about is going to lie somewhere in between the two. So we're going to weight the observations in a way that, for example, most recent data has more weight compared to the very far data in the past, right? So we're going to give more weight to more recent data set. And we're going to call it exponential smoothing method. So again, this is somewhere in between exponential smoothing. And you will see where the name exponential is coming from, right? Methods. And again, these are nothing fancy, but weighted simple averages. So as I just said earlier, this module is all about moving averages, right? Now, we can think of it as a simple moving average. We show it with SMA, or exponential weighted moving average, or EWMA. And if you have done some technical analysis for financial time series, you're pretty much familiar with these things, and you know that we call them indicators, right? So indicators. So these are technical indicators. Basically, they're going to look into historical data and then give you a summary statistic based on different statistical formulas, right? And I'm going to actually show it on a graph, and it makes sense what we're talking about. So here we're going back to our airline passenger data set between 1949 and 1960. But this is monthly data. So the blue line is the actual data. And now I'm showing two moving averages. One is simple moving average. We're going to show it with orange. Let me actually pick the orange color. This is my moving average, and the window that we're using in this example is just 12. So this simply means that at each point in time, look at the previous 12 observations and take the average. And take the average, and that's going to be the value for your moving average window 12. And you're going to roll it over, right? So it makes sense. It's going to make more sense if you look at this data. So here, we're at the beginning of the time series, right? And as you can see, for the first 11 observations, there is no value for MA 12, right? So the orange line starts from here. So this means that as soon as we get the first 12 observations, all of them, we're going to take the average and report that number, and that number is going to be here. Okay, so that's why your simple moving averages with window 12 is going to start from observation 12 and not earlier, right? And this means that at any point, so for example, if I'm here, it's going to look at the past 12 observations, take the average, and this value here, well, actually, let's keep it like this. This value here is going to be the average number, right? All right, so this is simple moving average, and which is going to give equal weights to all the 12 observations. So let's say equal weights versus exponential weighted moving averages, which is going to give different. So exponential weighted moving averages. And again, window is equal to 12. So this is going to give different weights. So different weights to each observations, right? And basically, it's going to put more weights on the values that happened more recently. And that's why it starts from the very first observation. So in the very first observation, we're going to say, okay, we don't have historical data. We don't have the past 12 observations, but I have one observation. So that's going to have the highest weight. So that's why this thing is going to start from the very first observation, exponential weighted moving averages. And then the 12. And then when we get the second observation, so it's going to be average between first and second, giving more weights to the second observation. 10th observation, the average between 1 to 10th, giving 10 and 9 more weights compared to the initial observations. And then until we get the full window of 12, and for example, if you are here at the very end, I'm here, this is where my cursor is, it's going to look at the previous 12 observation, give more weights. So think of these bars as weights, right? It's going to give more weights to more recent observation and take the weighted average. And that weighted average is going to be this number. So because exponential weighted moving average indicator is going to put more weights on the more recent data, this means that it's going to reduce the lag effect from SMA, right? So because simple moving average, again, let's go back to this observation. If I want to do simple moving average, so it's going to give the same weight to all of them. If it gives the same weight, once the data, let's the passenger data is high here, it's going to give it the same weight. So that's why it's a little lagging. I'm taking the average of all these observations, and then the average is small, right? But for exponential weighted moving averages, it's going to give the most weight. Let me use my laser. It's going to give the most weight to this observation. That's why your exponential weighted moving average number is going to be higher. So this basically means that EWMA is reducing the lag effect from SMA. So what are these things? Why am I talking about it? So these are simple indicators. Later on, we're going to build models on top of these indicators. Well, actually, we start with methods. We call them exponential smoothing methods. And now you know that it's nothing fancy. It's all about a weighted average of some observations. And after that, in the next video, we are going to talk about, okay, so these methods are going to give us some point forecast into the future. How can we make prediction intervals? So we're going to introduce, we're going to add the noise, make some assumption for that residuals, and then call it ETS models. With the ETS models, we should be able to create some confidence intervals as well, something like this. So again, we saw this already before. So imagine this is your point estimate and your confidence interval. Let me actually do it yellow again. It's going to be something like this. So ignore the blue one. So let me see if I can erase it. Yep, there you go. There you go. Pretty good. Okay, so here is another example. Now we're using Apple stock price between 2018 and end of 2023. So the blue one is Apple stock price daily prices. Yeah, I assume it's adjusted close. And the orange one is moving average. Now our window is 100. And the green one is exponential weighted moving averages, and the window is 100. So if I want to, so let's actually use the right color. As you know already, the exponential weighted moving averages start from the first observation, but the simple moving average is going to start from observation number 100. So this is going to be observation number 100. Okay, so this is day 100, and as you can see, for SMA, we are losing these first 99 observations, right? So let's call it data loss. Data loss. So this means that as you increase the window, the SMA might not be necessarily a good indicator to look into, because again, you're losing valuable information at the beginning, right? So that's why mainly we're going to focus on exponential weighted moving averages. And that's exactly what we're going to do in this module. So we say, hey, this is a methodology. Now we know what is exponential weighted moving averages. We are giving different weights to different observations, more weights to more recent observation. Now let's go ahead and break down these time series into their components and say, for example, each component can be written as an exponential smoothing average method, right? So that's basically what we're going to do in the rest of these slides. All right, let's wrap up this short introduction before we move forward with the methodologies and the models. So exponential smoothing, the concept was proposed in late 1950s by Holt, Brown, and Winter. And these methodologies has motivated some of the most successful forecasting methods, right? Guys, remember, these were simple indicators. Then we're going to extend it to methods, and then finally extend it to models, right? And a forecast generated by exponential smoothing, as we said, it used weighted average of the past observations, which weights are going to decay exponentially over time, right? In other words, more recent observations have higher weights. So what we're going to do for the rest of this video, we're going to actually first start with, we present the mechanics of the most important exponential smoothing method, And as I said earlier, these methods are going to give you point estimate. So let's say these are the point estimate. And then we're going to expand this idea going from methods to model by making some important assumption about the residuals. We say the residuals are normally distributed. So we're going to put together some statistical models that can create exact same point predictions, but at the same time, it will give you some prediction intervals as well. So that's a roadmap for the rest of the video. Okay, this concludes our part 0 introduction to smoothing methods versus ETS models. In next part, we call it part 1, we will talk about exponential smoothing methods. And in part 2, we're going to cover basically exponential smoothing based models, or ETS. These are models. And then finally in part 3, we're going to cover everything that we've talked about in the theory lectures in Python, and we're going to use PyCaret package. Until the next one, take care. If you're looking to stay updated with the latest versions of the course's materials, please make sure to follow my GitHub and remember to refresh your repositories periodically. If you find yourself needing a bit more background in econometrics, machine learning, or deep learning, check out my other YouTube videos for additional insights. And for all the latest news and quick updates, don't forget to follow me on Twitter. Thanks for joining me, and let's keep learning together.